So, although it doesn't seem like too long ago, we're already looking back at the good old days in Chem 305. And in the good old days, we would say that if you had 22.4 liters of any ideal gas, which is any gas in this chemistry class, 22.4 liters of any gas equals 1 mole of gas particles. But one of the stipulations was this relationship only occurs at STP conditions, standard temperature and pressure. So since the world does not exist at 0 degrees C and 1 atmosphere of pressure all the time, we needed a different way to convert, for instance, volume to moles, as well as taking some other considerations into effect. So we have this equation, and this is known as the ideal gas law. So what I'd like to do quickly is just tell you what each of these variables represent and the units that you'll use for them. P is pressure. And pressure, the operative units, is atmospheres. And more on that in a minute, but basically an idea is an atmosphere is the amount of pressure that you experience at sea level. So the force the atmosphere exerts on you at sea level, that is 1 atmosphere. Okay, so there are other units though, and 1 atmosphere is our base unit, but that equals 760 millimeters of mercury. And this millimeters of mercury is extremely common. And it was the first of the units, millimeters of mercury was one of the first units used to study atmospheric pressure. So it's persisted today. Another thing, instead of millimeters of mercury, 1 atmosphere equals 760 millimeters of mercury. That also equals 760 torr. So torr and millimeters of mercury are, for all intents and purposes, interchangeable. But you'll sometimes be given these units, and you have to convert them to atmospheres, since that's what we use in our equation. Okay, so unless there's any questions about that, V is volume, and the units we want is the liter. The unit we want is liter, and of course, you need to convert to liters if you're given a different unit. N equals the number of moles of gas particles. And its unit would be obviously the mole. And sometimes you have to convert to moles. And all of you have converted to moles. I mean, I know that's something I've made you do many times, so you realize that that isn't always the unit you're given. Okay, R is actually not a variable. It's known as the gas law constant. Gas law constant. And it equals 0.08206 to 4 sig figs. And it has crazy units. The units are liters times atmospheres over moles times Kelvin temperature. If you see 0.0821, that's the same number to 1 less sig fig. That's what they use in the book a lot. All right, the last one is T, and as you guessed, that's temperature. And as you see in the ideal gas law constant, Kelvin is our operative unit. So make sure that this sticks in your head. If you use Celsius in the gas law equation, you'll get the wrong answer. You have to use Kelvin. So oftentimes you have to convert to Kelvin. So just as a reminder, Kelvin equals 273 plus degrees C, or degrees C plus 273. That's how you get the Kelvin temperature from degrees Celsius. All right, so again, if you're ever wondering why if you're using the gas law and you're not getting the right answer, make sure that the values you plug in are in these units. All right, well, more on that when we start doing the math later. let's talk about what your math teacher would want to come in and do a bit of a guest lecture about. So whenever you have an expression where you have multiple variables and an equal sign, they're variables that we say have an inverse relationship and a direct relationship. So notice how some variables are on the same side of the equal sign and then others are on opposite sides of the equal sign. If you're on the same side of the equal sign, same side of equals sign, that equals an inverse relationship. And an inverse relationship, you would say, as one goes up, the other goes down, or vice versa. Opposite sides of the equal sign are direct relationships. So if they're on opposite sides of the equal sign, that's a direct relationship. And that means as one goes up, the other goes up. As one goes down, so does the other. Okay, so now it just wants you to pick apart this equation really quickly and say which ones have direct and which have inverse relationships. So let's start with the ones that are on the same side of the equal sign, like pressure and volume. So we would say P and V have an inverse relationship. Do any other variables have an inverse relationship? Remember, R is not a variable, so we can't use that. R is a constant. There's one other pair. N and T, right, on the other side of the equal sign. N and T. So again, if pressure goes up, volume will go down, and if volume goes up, pressure will go down, and likewise with number of moles and temperature. All right, now let's look at the ones that have direct relationships. Pressure and number of moles. So if you increase the number of moles of a gas, you're going to increase the pressure. Or if you increase the pressure, chances are the number of moles has increased. So P and N. But also pressure and temperature. If the pressure goes up, the temperature goes up. If the temperature goes down, the pressure goes down, and so on. What other pairs of variables have a direct relationship? What about with volume? Yeah, volume and number of moles. If you put more moles of gas, the volume will increase. Just like when you blow more moles of gas into a balloon, the balloon expands, right? So we know more moles, more volume. And then also volume and temperature. If you've ever put a dark colored balloon in the sunlight and it's already blown up, sometimes it will pop. It happens at my son's birthday party. He loves dark blue, and we went out and got him a bunch of dark blue balloons, and then just spontaneously as they're in the sunlight they started popping because they expanded. Yeah, they heated up fast because they were dark. All right, so that's the idea. Now we're just going to look at some very straightforward questions, and these types of questions will be on your exam. So these are those questions that you read them, you either know it or you don't, and you can answer it in just a matter of seconds and save your time for the more challenging questions. So what it's asking is whether or not the pressure of a gas in a sealed container would increase or decrease if these changes happened. So the volume is changing from 250 to 500 milliliters. So that's what's happening to the volume. Is this the volume increasing or decreasing? It's increasing. It's getting bigger. So the volume's going up. So what would we expect to happen to the pressure? Here, I'll write the... Yeah, you'd say pressure and volume are inversely proportional or have an inverse relationship because they're on the same side. So volume goes up, pressure goes down. Temperature goes from 20 to negative 80. So that's the temperature going up or down? Down, yeah. Seems obvious, but it's worth asking. Okay, so if the temperature goes down, what's going to happen to the pressure? Yeah, it's going to go down. They're on opposite sides, so they'll do the same thing. They're directly related. All right, the moles of the gas go from 1 to 1.5. So that's getting more moles. So if N goes up, what happens to P? Yeah, it goes up too. All right, so you guys all got 3 points out of 3 points there. Now this is the same question. We're just asking for changes in the volume now. So it says the pressure goes from 775 to 705. Is that going down or up? Down. So if the pressure goes down, what happens to the volume? PV equals nRT. So if you're on the same side of the equal sign, if one goes down, what happens to the other one? Goes up. Yep. All right, the temperature goes from 15 to 60, so that's going, temperature's increasing, going up. So what happens to my volume? It goes up as well, opposite sides of the equal sign, direct relationship. The moles of a gas inside double. So double means to multiply by 2, right? To have twice as much. So that means N, the number of particles, is going up. So what happens to V when N goes up? It goes up too. All right, so out of these 6 questions, hopefully that's 6 out of 6 points. And you save your time for when we do math. All right, now really quickly, atmospheric pressure is really hard to describe because you can't see it. And since you felt it from the moment you were born, or maybe even when you were in your mom's womb, you don't really feel it. It's like a fish. Do they know that there's water there? Because they've always experienced it. So until it's gone, they tend to not notice it's there. Well, atmospheric pressure is very, very real, and its cause now is very well known. So let's draw my stick figures here, since my art skipped a generation. My daughter's far surpassed me by the age of 4 she had. Okay, so here is you, and here you are, and you're at sea level. Above you and all around you in 360 degrees are gazillions and gazillions of gas particles. I haven't even drawn nearly even close to enough. And they surround you, and they go way up into the sky for miles. And each individual little teeny tiny gas particle is so small it's imperceptible. But when you have so many gazillions of them all over, it's like a blanket weighing you down. And this pressure that we talk about, that 760 millimeters of mercury, you are literally feeling the weight of that blanket of molecules and atoms squeezing you and pressing on you. That's what atmospheric pressure is. And it's simply the combined mass of all these little teeny tiny particles pushing down on you. All right, so that's at sea level. But what happens if you take a trip and you climb up to the top of a mountain? Now, obviously, this is not to scale because, you know, this person's what, maybe 6 foot tops. You know, this wouldn't be much of a mountain. It'd be more like a skateboard ramp. But pretend this is a mountain. So let's say, you know, they're at, 9,000 feet. Not so high, but pretty high. How come, the question is, why does the atmospheric pressure decrease at higher elevations? Maybe you know, or maybe you can look at this picture and figure it out. So why would a person standing on the mountain not experience as much pressure as someone standing at sea level? What's that? Yeah, that's exactly right. They're higher in the sky. And when they're up here, then there's less particles that can push down on them. See, they're not getting pushed down on the particles that are below them, just the ones that are atop them and kind of all around them. And so because when you're at the higher elevation, you simply have fewer particles above you, you have less pressure. That's why your ears pop. That's why when you go to the convenience store and you look at a bag of potato chips, it's like completely expanded, like you just want to come up and pop it, right? So that air is pushing the bag out because it's under less pressure. Okay, so that's the reason why pressure decreases at a higher elevation. There's just less particles above you because now they're below you. But it's worth talking about just briefly a condition known as the bends that happens from pressure underwater. So here's our sea level, and we forget that you can go below sea level if you especially if you go under the water. So you have the atmospheric pressure pushing down on the sea, and then let's say now you're under the water. And just to show that you're not dead, we'll put some fins on there so it's not, just a body floating around. You're in little scuba tanks. Okay, so you're floating around there under the water. and you are experiencing all the pressure that the atmosphere is pushing on you. It's being transferred through the water, but far in excess of any pressure that atmosphere is pushing on you, you also have the pressure due to the water itself, which is quite a bit. Now, when you are under this much pressure, and by the way, we're not talking like, Jacques Cousteau level depths down in the Marianas Trench. We're talking about like 30 feet, 15 meters. We're not talking super, super deep. But you can experience far in excess of double, triple, quadruple atmospheric pressure. So what happens? Well, you breathe, and you're breathing all the time now, and when you have these tanks underwater, you're also breathing. And gases dissolve in your blood. So what happens is when you're under really, really high pressure, just like any sort of pressure situation, the gases will equalize to that pressure. So if you have gases in your blood at high pressure, the high pressure is keeping those gas particles small and dissolved. So right now we have high pressure. And so that's the equilibrium or the stasis that your blood and your gas are in. But then what happens is if you are taken to a low pressure situation too quickly, these gases start to expand. And what you have is a rupturing in your blood vessels. As the gases expand, they pop your blood vessels, and basically you die an extremely painful death as you bleed to death inside of yourself. And that condition is called the bends. It's probably one of the most painful ways that you can go. And unfortunately, this isn't something that happens, once every 20 years. There's a known number of deaths that will just happen every year because of this. So what it means is that if you're scuba diving, and I'm sure all of you who will scuba dive or have scuba dive would go through a lengthy certification process, a lot of it is involved in getting you from below water to the surface safely. Now, what can happen is if you're down deep under the water and all of a sudden there's an emergency, like you start running out of air, you're attacked by a shark or something like that happens, then, you have a choice to make. Do you want to, perish down below the water? You want to get brought up and deal with the bends? Well, what happens is if you are experiencing the bends, your only hope is that they have what's called a hyperbaric chamber, which means super high pressure chamber. So what they can do is try to throw you back into a high pressure chamber, squeeze these gases back into a smaller volume, and then slowly, little by little by little, bring you back to regular atmospheric pressure, and then your body will have time to adjust it and get that excess volume of air out of your body. So anyway, that's the chemistry behind this condition known as the bends, and something that if you ever go scuba diving, you'll hear more about. Now, I didn't put a snorkel on this person because no one's going to be able to dive deep enough snorkeling that this would ever be an issue. If you were able to dive that deep and have like a super, super long snorkel, you wouldn't be able to exchange the air enough to get enough air to breathe. So that wouldn't be your issue. All right. So that's the bends. All right, so more about atmospheric pressure. So we're talking maybe like 500-600 years ago, they're starting to realize that there's this mysterious force, this mysterious pressure that was all around us, and they started to invent the most primitive of the barometers. So what you see here is a barometer, and I'll tell you how it works. And it's an instrument that measures atmospheric pressure. Now, this says pressure. Now, this is the old school rudimentary barometer, but quite honestly, barometers haven't really changed. The only thing that's different is now you probably won't find mercury in it. Not in this country anyway. Mercury is very, very hard to get, and it's extremely toxic, so that's why they don't want you to have it. A lot of times they think they use alcohols, maybe water even. But the idea is that if you have a glass tube or a column, it doesn't even have to be glass, it just has to be capable of withstanding a vacuum. So inside this column, there's not even air. There's nothingness inside this tube, and that tube is placed inside the mercury, or any liquid for that matter. And what happens is the atmosphere, all these particles that we've talked about, are exerting their force on the surface of this pool. And what happens is that forces the liquid squeezes it down and pushes it up this tube. And 1 atmosphere of pressure is enough force that it can lift a column of mercury 760 millimeters, 76 centimeters, right? So this mercury, as long as the pressure doesn't change, it's like keeping your finger on it, you're keeping that liquid mercury up in that column. Now, if all of a sudden we took the atmospheric pressure away, this would fall back down. But to give you an idea of how strong the atmospheric pressure is, mercury obviously is quite a bit more dense than water, almost 14 times as dense as water. Do you know how tall a column of water the atmosphere could hold? Over 30 feet. Over 30 feet. So if you have a fish pond and you want to be the awesome fish parent on the block, consider doing this. I don't have a fish pond. I did this with a fish tank, and I had golden barbs. I didn't have goldfish, but they did the same thing. What someone has done is they've taken this large prism, and it's open on one end, and they filled it full of water and then tipped it straight up. Now, the reason why the water isn't spilling out of here is, like I've shown, the atmospheric pressure is pushing on the surface of this pond and keeping the water elevated. This column could be about 30 feet tall, and it still would be held up by atmospheric pressure. It's pretty amazing. Now, one thing is fish are kind of like, anything. There's a whole range of fish, from like fish that just kind of eat and blink at you, to fish that actually, if you have a pet fish, they'll interact with you, and they're like excited when you come home and all that, and they recognize people. So goldfish, I don't know where they are on the scale of fish intelligence. They seem somewhat smart, although I've had several, and I can say some are smarter than others, but they will do this amazing thing. If you make a column of water above a tank, fish will tend to swim up and start looking around. Now, I could imagine why a fish would want to do that, because think about the history of fish. Do they even know that anything other than water exists? And all of a sudden, they get this like penthouse view, and they can actually see, like, oh my God, there's this whole world out here. I mean, if I were a fish, I'd want to do that. And it's interesting, when I wish I had videoed it, but this happened probably 15 years ago. I had some golden barbs, and I had a big fish tank, and I gave them this sort of situation, and one of them swam up there and figured it out. I was like, whoa, and then it swam back down and looked around, and it went back up and tried it again just to see that it wasn't a fluke. And then it started going down and herding the other fish, like, come on, guys, you got to see this, check it out. And little by little, it ushered all the fish up into the column. So anyway, yeah, if you want to be an awesome fish parent, try this out. But don't forget to explain the chemistry behind that to your friends so that you can justify it as a legitimate experiment, not as just some freaky thing that you felt like doing. Okay. Sorry to ruin that imagery with math, but let me again remind you of the good old days. How many moles of hydrogen are in half a liter at STP? And you'd say, oh yeah, half a liter of hydrogen? Well, if I have any gas, 1 mole of that gas is when I have 22.4 liters, and you'd quickly tell me how many moles that would be. 0.5 divided by 22.4, and you'd say that is 0.0223 moles of hydrogen, and life would be good. But that was because we were at STP. So I really want to stress that this is how this chapter is discretely different than how you know it from before. Now we're not at STP. The pressure is 3.35 atmospheres, not 1 atmosphere, and it's not 0 degrees C, it's quite a bit colder. So now we have to use our ideal gas law equation. It's an occasion to use this equation, and it's PV equals nRT, and I've heard it referred to as PivNert, but if you say I was using PivNert, and I've heard that before, and you say the equation PV equals nRT, you say I was using PivNert, I'd like, is that illegal? I don't know what that is. So I've heard that. So I don't know when you say PivNert what that is. But anyway, that's PV equals nRT is the ideal gas law equation. And this question asks us to solve for moles. So what I'm doing is I'm looking at this problem. I'm not really even addressing it yet. I just want to see what it is I have to solve for. Moles. So what I like to do is find the variable I'm solving and then isolate it using algebra. So I'm going to divide both sides by RT. and it cancels out over here, and what I end up with is N equals PV over RT. Now the reason I do that is I like to have the equation ready just to plug in the variables once I find them out. So what I'm going to do is I'm going to list them off. You can do this if you want to. I'm doing it mostly to help you guys see where I'm finding this information. P is 3.35 atmospheres. That's the pressure. But if you have never done this before, I would highly recommend doing it the way I'm showing you. Write the equation out as algebra, as variables, then list the values for each of those variables and then just plug it in and solve. Volume is given as half a liter. And what's important is I'm making sure that the units that we have are what I need for my equation. R is a constant, we already know that, and then T is negative 75 degrees C. But I need Kelvin. I have to change that. So Kelvin is degrees C plus 273. So let's see what that is. I got 198 Kelvin. All right, and then R is 0.08206. Just to remind you. Okay, so now I have all my values. Let's plug them in. So I didn't leave tons of room, so I'm not going to write the units this time. P is 3.35 atmospheres. Volume is half a liter. R is the constant. I think I give that to you on all the exams, so you don't need to memorize that constant. And if I don't give it to you, just ask me, I'll write it on the board. And T is Kelvin temperature is what we need, so we write 198 K. All right, so let's see what we got. I got this would equal 0.103 moles. I'll leave more room down here and I'll show you how the unit cancellation works. But N's unit would be moles, so that's what we're solving for. All right, so I'm assuming since no one's objecting that at least a handful of you have gone over my math and made sure I crunched all the right numbers. Okay, so let's look at another one here. PV equals nRT is our equation. So again, I want to figure out what it is I need to solve for. Temperature. I'm solving for T. So T equals PV divided by nR. So here's my equation. Now, again, what I recommend doing is writing down all the variables you need and making sure they're in the right units. So I need pressure, and pressure is given as 655 torr. So pressure equals 655 torr. I want you guys to recognize that I don't need torr, I need atmospheres. So the conversion is 1 atmosphere is 760 torr. And that's 0.8618 atmospheres. So 0.8618. Okay. We need volume, and that was given in the problem as 3.5 liters. We need N, and N was given in the problem as 1/4 of a mole. And we need R, which is always 0.08206 liters atmospheres over moles times temperature in Kelvin. So what I've done again is I've found all the variables I need. I made sure they're in the right units, and now, hopefully, it's as simple as plugging those in to this equation and having it work out. So pressure, I'll use the units this time, 0.8618 atmospheres. Now notice I kept an extra sig fig, and even better yet, I kept that whole value in my calculator, and I'll use that. Okay, volume is all we have listed here, 3.5 liters. Number of moles in R, 0.250 moles, and R is 0.08206 liters times atmospheres over moles times Kelvin. All right, so how does the units cancel out here? Most of them cancel with R. So atmospheres divided by atmospheres, liters divided by liters, moles divided by moles, and now we have Kelvin in the denominator of the denominator. So trust me now, believe me later, the denominator of the denominator is the numerator. So what that means is that this unit of K ends up being in the numerator. Here's the proof. Here's what your algebra teacher would say. 1 over x equals x. That's what your algebra teacher would tell you. Okay, so that's why this unit of Kelvin down here works. So let's see what we got. I kept this whole value in my calculator from before. I got 147 Kelvin. Now the problem didn't specify whether or not to provide the temperature in Kelvin or degrees C, but if I said degrees C equals Kelvin minus 273, then if it wanted the temperature, we would list it as negative 125 degrees C. So that is fine, and that is fine as an answer. And the problem will specify for you which temperature unit to use. And if not, then use whatever you want. All right. All right, well, the good news is this is the last slide for today. Amen. Yeah. All right. So let's say you got hired on as a chemist. You're feeling good about your knowledge of gas laws, and someone said, all right, hey, we have a 25-liter steel canister, and I need 4 kilograms of nitrogen gas to be stored in that canister. What pressure is that canister going to have to withstand, right? Because you have a gas, it's going to exert a pressure. You don't want the thing that's holding it being compromised and exploding. So that's a pretty legitimate question. So the question is basically solve for the pressure of the nitrogen gas. So PV equals nRT. So let's start just kind of brainstorming here and looking at what we're asked to solve. So pressure, we don't know. We're being asked to solve for that. Volume we're given is 25 liters. N, more on that in a minute. R we know is 0.08206 liters, atmospheres, moles, Kelvin. And then temperature is room temperature, 20 degrees C. 20 degrees C, which would be 293 Kelvin, because I just added 273 to 20. So N, we don't have moles given to us in the problem. What would we do about that? We're missing N, but yet we're asked to solve for P, so I can't ignore N. I need a value. Yeah, it gives a mass, right? So 4 kilograms is 4,000 grams. And then how would we convert grams to number of moles? You remember that? A hint? Yeah. We need to know the mass of nitrogen gas. Okay, so we have to remember, first of all, that nitrogen gas is N2. and N2 equals 28.02 grams for every mole. But that's what number of moles is, right? Number of moles, N, is equal to your grams of whatever you have divided by molar mass. So let's just say that this is my abbreviation for molar mass, right? That's what number of moles is, grams divided by molar mass. So you know where this is going. I like algebraic substitutions. If N equals grams over molar mass, wherever I see an N, I can insert grams over molar mass. So let's do that. PV equals, instead of N, I'm going to do grams over molar mass times RT. I just switched out that N. So now I've provided you a new version of the gas law that uses grams and molar mass in there. So you could start off and convert kilograms to moles, plug that in, and use PV equals nRT. Or if you're like me and like just a one-stop shop with an equation, this is how I would do it. But regardless, the question asked us to solve for pressure. So pressure is going to equal GRT over the molar mass, and then I have to divide both sides by volume. So volume. All right, so now I can just plug in my units if they're correct. So my grams, I hope you guys are okay with me saying 4 kilograms is 4,000 grams. Right, that's what kilo means, 1,000, so 4,000 grams. R is 0.08206. I'm leaving out the units just to save space and time. Temperature, we calculate as 293 Kelvin because we need Kelvin, not Celsius. Then we divide by the molar mass, which is 28.02. And then the volume, which is the 25 liters given in the problem. All right. And I get 137 atmospheres. I think the steel canister should be able to withstand that pressure. By the way, if you want liquid nitrogen, you would rent or pay a deposit, and yeah, you can get liquid nitrogen delivered to your house. You saw how much fun we had with it in the classroom, yeah. But just make sure that you rent a capable container. You don't want to have some sort of weird liquid nitrogen, I won't say explosion because there wouldn't be a fire, but yeah. So I think that would hold it. So any questions about this? We're about to do the same thing on the next problem. So let's take a look again at my derived equation. We had PV equals nRT, and then I changed that to PV equals grams GRT over molar mass. So perhaps you'll see the method to my madness here. This question says how many grams of krypton gas, and then gives you some parameters there, but it's asking you to solve for grams. So here's my grams I'd like to solve for. So I need to multiply both sides by molar mass, and I need to divide both sides by RT. So grams equals molar mass times pressure times volume divided by RT. But the whole reason I'm doing this is I like to have just an equation that I can plug in my values and then I get an answer. I don't really want to have to think about it a whole bunch. I just want to plug in easy to find values. Okay, so the molar mass, let's start with that. The molar mass of krypton we would get from the periodic table. Now, krypton is not one of those diatomic molecules like chlorine or oxygen or nitrogen. It's just single atoms of krypton. So its molar mass is right there, 83.80. And molar masses are grams per mole. Okay, we also need to know the pressure and the volume. So the pressure is 775 millimeters of mercury. But of course, that's not the units we need. We need atmospheres. So we convert that 1 atmosphere is 760 millimeters of mercury. So it's going to be a little over 1 atmosphere. 1.0197. And we'll keep a few extra significant figures beyond the 3. Although I'm still going to try to keep that whole number in my calculator. Okay, so that's our pressure. We need our volume, and that's given in the problem as 2.5 liters right here. So 2.500 liters. And we need R, that's always the same thing, 0.08206 liters, atmospheres, moles, Kelvin. And then temperature is 20 degrees C, which is 293 Kelvin when you add 273. And that's room temperature, is 293 Kelvin. All right, so I have all the values now to plug into my expression. So grams would equal the molar mass, 83.80 grams per mole, times pressure times volume. So my calculated pressure, the atmosphere is 1. 2.500 liters. That's the volume. This says 2.500 liters right there. Divided by R, 0.08206 liters, atmospheres, moles, Kelvin. And then temperature is 293 Kelvin. Okay, moles cancels out there and there. And let's see, liters cancels out. Kelvin cancels out, atmospheres cancels out. We're left with grams, which is what we want. Okay, so that equals I get 8.89 grams of krypton.